Hello friends, this is only using transistor circuits and today I'm going to talk about PWM signals. So my major concern of making a PWM generator is to control a servo motor. But for that, to design that circuit, I need to understand what is a PWM signal. So first I will show you. In short, I will explain you what is a PWM signal. So PWM stands for pulse width modulation, PWM signal. So a PWM signal is basically a square wave signal of a fixed frequency that depends on your application. The frequency depends on your application. So this is a square wave signal, this is time, and this is voltage V. Suppose our maximum voltage is 5 volts and minimum is 0. So we are generating a square wave, and in this square wave we are controlling the on time. We are controlling the width of the pulse, and that width of the pulse we are changing. So what happens when we change the width of the pulse? It's on for half the time, or we can completely on for a full time period. So what is the time period? The signal is repeated after a certain time. You can see the same signal is repeating. It's a periodic signal. So that the moment that it repeats, from the moment it starts, it's called time period. So it's denoted by capital T, and this time for which it is on is called T on, means for the time for which it is on, and this time for which it is off, it's called T off. So we denote this time T on by a term called duty cycle. So duty cycle is in percentage. It is in percentage and it's given by T on upon T on plus T off, which is nothing but the time period T. T on plus T off is T. T. So it's into 100. So that gives us our percentage duty cycle, and this is nothing but T. So for the percentage time it's on, it's called a duty cycle, and the PWM signal is very useful to signal generator is very useful in digital communications. It is used to convert analog value into pulse modulated code, pulse width modulated signal, and you can then transmit this signal through a optical fiber cable or a simple wire. So how does it affect the output voltage? So when we put this PWM signal through an integrator, we get for half the time it's on. That means the voltage through the integrator. The integrator is basically a low pass filter. So it averages the signal. If you average this signal out, suppose it's on for 50% and it's off for 50%. If you average out this signal, we will get a 2.5 volts at the output. And this is an integrator or a low pass filter. And here we have a square wave PWM signal generator, our PWM signal, and then we integrate it. Suppose it's a 50% duty cycle. 50% means it's half, for half the time it's on for T by 2, and it's off for T by 2. So that was the short theory. Now let's see the signals we require to control the servo motor. So the servo motor is actually a system in itself. It is a closed loop system. So whenever we give a PWM signal to it, if suppose it's at 0 degree and we give a PWM signal to it, so the PWM signal creates an error and the motor moves in a direction to cancel out the error, and when the error gets cancelled it stops, and at that angle it rests. So what we get is we get to control PWM signals, and the PWM signal actually control the angle rather than the speed. So we want servo motor, and it's basically a very high torque motor. So we can pull a string with it. We can control various latches, door latch. We can pull, in robotics we can pull the robotic arm, and all such things we can do with it. So let us see the signals that we require to control the servo motor. So we generate a 1 millisecond uh, pulse followed by a 19 millisecond off time, and the total time is uh, t is equal to 20 milliseconds. So if we divide 1 by 20, we will get frequency. I mean, 1 by time is equal to frequency, and that is equal to frequency. So 1 by 20 is equal to 50 hertz. So we need to generate a 50 hertz signal. We need to generate a 50 hertz signal in order to control the servo motor. So when we have a 1 millisecond on time, the motor position is at 0 degrees. So this is the shaft, and now it is at 0 degrees. So as we go on increasing the pulse width to 2 milliseconds, and this time period is constant, 20 milliseconds. So when we go on increasing this pulse width to 2 milliseconds, from 1 millisecond to 2 milliseconds, we get to rotate this servo motor from 0 to 180 degree. So if we generate a timing signal of 2 milliseconds on time and 18 milliseconds off time, and that we go on generating this signal 2 milliseconds. So the motor will rotate completely at opposite direction to 180 degrees. So this arrow, the motor will quickly rotate to this position if we directly generate from 1 millisecond to 2 millisecond. But we slowly vary this. So we want to design a circuit that the potentiometer varies the duty cycle. So let's calculate the duty cycle. T on is equal to 1 millisecond. So T on upon total time, which is 20 milliseconds, will directly substitute T on is equal to 1 milliseconds, and total time is 20 into 100. So 1 divided upon 20 is 0.05 into 100. So that gives us 5% duty cycle. So 5% duty cycle, 5% duty cycle, the motor is at 0 degrees. And let's calculate this. 2 upon 20 into 100, which is equal to 2 upon 20 is equal to, I think, 10%. So from 5% duty cycle to 10% duty cycle, if you vary it, we'll get a angular shift from 0 degree to 180 degree. So that was the signal that we required. Now let's see the different ways to generate the PWM signals. So there are three different ways by which we can generate a PWM signal. First one is by using a microcontroller. Second one is by using operational amplifier. Third one is by using IC555. So if you have many output devices that requires a PWM signal, so you can go with this microcontroller option, and you can use a Arduino or any 8051 based microcontroller. So if you are using 8051, you need a good knowledge of timers to generate a perfect delay of 1 millisecond and 19 millisecond, off time of 19 millisecond and on time of 1 millisecond to vary the duty cycle. So if you are using Arduino, they have got one library called servo.h. So this library makes it easy to control a servo motor. But if you don't want to use this library, you can use delay microsecond function to generate time signals in microseconds. So you can generate 1000 microsecond signal followed by a off time of 19,000 microseconds to control a servo motor. And what I am interested is not in this microcontroller part, because that will be another video. I am interested in these two things, which is made by using op amp and IC555. So let's discuss this op amp part. So we are using op amp in comparator mode. So at the end we have got one op amp which is in comparator mode. So we are comparing basically a triangular wave with our reference voltage that we are going to vary the potentiometer to control the output. We will get a PWM signal that we can connect to our servo motor or any device like a LED, or we can, yes, so we can vary the voltage with a potentiometer. So how we generate this triangular wave? We actually basically integrate a square wave of 50 Hertz because we want 20 millisecond pulse width, a 20 millisecond time period. So we integrate the square wave by using a resistor and a capacitor network, which gives us a triangular wave. So that we give to this comparator. This is how we generate a PWM signal. So to understand how this works is, this is a triangular wave, and suppose our voltage is varying at 3 levels. This is a comparator voltage. So suppose this line goes up and down. So I will show you. So at this time the pulse width is minimum, and at this time the pulse width is this much, and at this time the pulse width is this much. So by changing the voltage, that this is this voltage, we get a varying duty cycle. This is how the comparator based PWM generator works. In the 555 based PWM generator, in this we control the charging and discharging time in a stable multivibrator so that we get perfectly timed signals. So I'm going to show you how this 555 based and op-amp based PWM generator works in the simulator. So let's head on to the simulator to see how it works. So now we are in the simulation app, and I have fed a triangular wave signal to this non-inverting terminal, and the varying voltage is fed to this inverting terminal, and the output, we will get a pulse width modulated output. So now let's hit the play button and see how the circuit works. So this is a simulation. You can see in the graph. So this is our reference voltage in orange, the voltage that we are going to vary, or our analog input, and this is a fixed the green signal. It is a triangular wave. It rises above the reference voltage and falls below the reference voltage, and you can see that the output stays high for that much amount of time. So now we are going to vary this potentiometer. So we are going to lower the voltage, and you can see that the duty cycle has started to rise, and it rises all the way to 100%. And now we will increase the voltage, go on increasing the voltage, and you can see that the duty cycle is starting to fall, and now it's nearly 0%. Yes, now it's 0%. So we get a duty cycle modulation from 0% to 100%, and that's good for controlling a servo motor because we want to control the duty cycle from 5% to 10%, and that also can be achieved. And also we can, if we have an analog input like a varying signal that varies slowly, so we can encode that signal into a pulse width modulated information. Now let us take a look at 555 based PWM generator. This circuit is similar to 555, a stable multivibrator circuit. The only difference here is that we make separate paths for charging and discharging with the help of these two diodes. So the capacitor charges through this diode and it discharges through this diode. The potentiometer, 10K potentiometer, is used to vary the charging and discharging time because ultimately we are controlling the RC constant, so which affects the time. And now We are going to run the simulation. So this 1 microfarad capacitor and 10k resistor determines the frequency, which is 50 Hertz. So that is what we require for controlling the servo motor. And why I have used this transistor I will explain you later. So I will run the simulation for now. And you can see right now yes, across this transistor we want to see the output at pin 3 of 555, and you can see this is the signal. And now we will vary this potentiometer. Now what we will do first, we will change the discharging time. So now we are changing the discharging time. So we will go on decreasing the discharge time, and you can see that the off time also decreases. So this is the minimum discharge time we can get, and maximum duty cycle. I think this is a 99% duty cycle, you can call it. That means for 99% of time the output is on. And now we will start to increase the discharge time. Now we will increase the discharge time to maximum. So this is a maximum discharge time, and you can see that we get a duty cycle of 50%. So the duty cycle is restricted to 50%. We cannot get higher than 50%. That is due to this 10k resistor, because the charging time has to be through this 10k resistor and charging this 1 microfarad capacitor. And this 10k resistor also fixes the frequency to 50 Hertz. So we cannot change this 10k resistor. So what we can do to get a duty cycle between 5% to 10% in order to control our servo motor. So here I have one solution. I have just inverted the signal. And we get a duty cycle variation between 50% to 0%. So earlier it was 50% to 99%, and now it's 50% to, this is I think 1%. So this is the minimum on time we can get, minimum duty cycle, and it's less than 1 millisecond. So we get to control the duty cycle from 5 millisecond, from 5% to 10% very easily by using this 10k potentiometer. And this is a good circuit to control the servo motor. So let's see how the circuit works on the breadboard and how it controls the servo motor. So let's move on to the practical. So here you can see a 555 based PWM generator made on the breadboard. So this is the potentiometer 10k pot that we are going to vary. These are the two diodes. This one is for charging and this one is for discharging. So this is a diode. Even though this is a LED, I've converted this LED into a diode, and I have made a video about it. So if you are interested, watch my previous video. So for now, this is a PWM circuit made. This is the output transistor which inverts our third pin output from this 555. This is a 1 microfarad capacitor. This is a 10k resistor. And now I will show you the demonstration. So this is actually a project which I have made. So I have used a servo motor to pump the liquid soap to make automatic soap dispenser. So I will rotate the potentiometer and you will see that the motor moves up and down. So now I will rotate it, and you can see that the motor is started to push against the pump. And in this way, if we go on doing it backward and forward, so we will get to pump the liquid soap out from the dispenser. So yeah, see what I'm doing here is I'm just varying this potentiometer and I'm getting to vary this servo motor. You can see that the soap is coming out from the dispenser. This is the project I made, and I also made a 19-second video about this soap dispenser which I made using Arduino, but later I modified by using a PWM 555 PWM generator. So this was the circuit, and if you're more interested about this soap dispenser, so how it works is when I place my hand beneath this, it interrupts the sensor, and that sensor actually turns off the output of this comparator, and which brings this two resistors in parallel with this potentiometer, which actually pushes the servo down angle. It brings angle down and we get this. So I'm just working on it right now. So this was the video. After the project is developed, I will definitely share it. So thanks for watching. This was the practical part, that how you can control. Basically it was just to how show you that it's possible to control a servo motor using a 555. So yes, thanks for watching. Like and subscribe this video if you learned something. Stay curious. Goodbye.